In the first video, we have seen what is hum. Let's quickly review it. Hum is this kind of sound, or this. This is a noise which adds to the normal sound, and of course we don't want to hear it. As you remember, in the first video we have seen several examples of hum sources. In those examples, hum came from electromagnetic field which is radiated from the several power supply sections. Also, we have seen hum coming from ground loops. In this new video, we will see other possible sources of hum, other than the radiated one from the power supply we have seen before, or the one coming from ground loops. Then we will see the solutions we can implement in order to avoid hum. Another way for the audio signal to pick up noise is through the preamplifier or power tube, mainly through the preamplifier tubes. If the anode voltage, so the high voltage, is not sufficiently filtered, so if we still have some ripple over the anode DC voltage, we might hear this ripple as hum on the audio signal. Let me just remark this. We're not speaking of the electromagnetic field radiated by the power supply sections. We spoke about that in the last video. On the contrary, here we are speaking about the high voltage ripple, which can sort of modulate the audio signal passing through each tube. Of course, preamplifier tubes are the most sensitive in that regard, so it's very important to provide a very clean anode voltage to the preamplifier tubes. But even some power tubes, especially if they are configured as single-ended, so we have a single tube taking care of the whole audio signal, which means this tube is in class A. Well, in this case, the anode voltage should be very well filtered. Again, otherwise we might hear noise due to the ripple on the high voltage. Other power amplifier layout, such for example the push-pull power amplifiers, are less prone to pick up hum because they have a very high power supply rejection ratio, which means that in case ripple is still present in the high voltage, then this gets zero, gets null by the opposite action of each one of the two tubes, or of the two tubes pairs, as in this case. Another way the signal can be affected by hum is through mechanical vibrations of the power supply transformer. Power supply transformer can vibrate. The frequency of those vibrations is 50 or 60 Hertz. In a properly made, built power transformer, those vibrations are non-existent, basically. But there might be cases when, again, those vibrations could affect the preamplifier tubes, mainly, especially the most microphonic ones. So especially the first preamplifier tubes, those which take care of the smaller signals. So we have seen which are the potential hum generators inside the chassis of each one of the components of each device. Of course, we also have potential hum induced by the external world. For example, if you think about a tube amplifier with a tube exposed, so mounted in the outside chassis, then of course they can pick up noise and hum from the outside world. So having said all that, which are the solutions we can deploy in order to design and build a completely hum-free preamplifier or amplifier? We will see several different solutions which altogether will contribute to a completely noise-free amplifier. The first solution is to implement a star ground. The objective is to minimize, to kill every ground loop. So according to this star ground layout, we should have a single grounding point, maybe at the center of the device. Each and every ground within the amplifier should have its own wire to the central grounding point. Of course, there are several degrees of precision. I would say extreme solution would be to have really each and every grounding connection within the amplifier with its own ground wire to the central grounding point. This will work for sure, but might be a little bit tricky to implement. Of course, we should utilize some common sense. For example, it might help collecting all grounding points within a single amplifier stage or preamplifier stage, and have just one wire, just one ground wire from that point to the central grounding point. You will need to experiment a little bit, but again, if you adopt the, I would say, extreme solution, for sure you will not hear hum. Even the ground side of the power supply capacitors should be connected to the same grounding point, with the exception of the first capacitor. The minus leg of the first power supply capacitor should be connected to both the central grounding point and the center tap of the power transformer. Then the chassis is connected to the star ground through a cable in one point only. It's very important not to have more connections between the chassis, the metallic chassis, and the central grounding point. Furthermore, the ground side of the signal input sockets, the RCA analog signal input sockets, for example, should be isolated from the chassis, and those should be connected to the central grounding point by a cable or through the shield of the shielded cable. Speaking of shielded cables, the ground, so the shield of those cables, should be connected to ground on one point only, on one side only. It's very important not to connect both sides of the shield to the grounding point, because otherwise we would create a ground loop. The safety earth within the power supply socket should be connected to the same star ground point through a separate cable. So we have seen how to break ground loops, so how to design an amplifier without ground loops. Now let's see how we can reduce the influence of the power supply ripple, speaking of high voltage, or the influence of the AC heater voltage. First of all, it's very important to properly filter the high voltage power supply. It's very important not to have more than, for example, 1 millivolt of ripple on top of the high voltage feeding the preamplifier or power tubes. Of course, this requirement, 1 millivolt, can be changed according to the circuit layout. So in case of very sensitive preamplifier tubes, maybe we will want to have lower than 1 millivolt ripple. And in case of power amplifier tubes, maybe even in a push-pull configuration, we can accept more than 1 millivolt ripple. We can even accept maybe 10 millivolt or something like that. So this should be adapted to the circuit. Nevertheless, generically speaking, it's very important to reduce the ripple to really the minimum we can achieve, and this can be achieved by the utilization of smoothing impedance on the power supply module and following stages of resistor and capacitor. In this way, I can reduce the ripple to a minimum, to the desired minimum. As the high voltage can still have some little bit of ripple, even if just 1 millivolt, for example, or even lower. What I do in my design is to shield the cables feeding high voltage to the preamplifier tubes. In this way, I avoid the ripple, even if it is that low, to be radiated in the environment, and in order again to avoid for the audio signal to pick up that ripple. Let's now speak about heaters voltage. My rule of thumb, which I built over the years, is the following. If we have preamplifier line level tubes or power amplifier tubes, then it's perfectly okay to go with AC heater voltage. On the contrary, if I have low level, very low level preamplifiers, such for example phono preamplifiers, then I strongly recommend to go for DC voltage for the heaters. Then, speaking about DC heaters, I suggest to implement a stabilized DC heater voltage, not just a voltage which comes from AC and then is rectified and filtered. Because if we do in this way, so rectify and filter, we still have a huge amount of ripple on top of my 6.3 voltage, for example. So this ripple can be heard, is very annoying, is 100 Hertz or 120 Hertz. So it can be really very annoying. So what I suggest is to stabilize the heater voltage if we decide to implement a DC voltage. Of course, this means that I need to implement a stabilizer integrated circuit which dissipates a huge amount of heat, so we need to deploy a proper heatsink. Another solution to get a clean DC voltage for the heater would be to rectify, filter, and then add a smoothing impedance, and then following RC filtering stages. In this way, I can achieve a sufficiently clean DC voltage for the heaters. But again, really, I don't recommend to just utilize a rectifier and a capacitor, because the ripple would be in this case too high. Speaking about AC heaters, it's very important to utilize shielded cables for feeding the AC heater voltage to the tubes. This is very important because the current flowing through those cables can be very high, in the order of several amps. Heater voltage, regardless if AC or DC, should be referenced to ground. This is very important. So in case of AC heater voltage, we can deploy a virtual ground and connect this to the common star ground point. Or better, we can reference this virtual ground, in case of AC heater, to a value, for example, 50 volt. In this way, we elevate the heater voltage respect to the cathode voltage, and this is very important in order to, again, reduce the hum picked up by the tube. Also, this is very good solution for sake of cathode to ether maximum voltage, which is an information you find in all tubes datasheet. Cathode voltage, in fact, cannot be much higher than the heater voltage in any given tube. Typical limit is 100 volt or 150 volt, depending on the tube. So for some circuits, for example cathode followers, we really need to elevate the heater voltage compared to the cathode voltage. Even if we have a DC heater voltage, I would suggest to elevate anyway, in order to again respect the maximum cathode to heater voltage, which you find in the datasheet for any tube. And this is valid for both AC and DC heater power supply voltage. Of course, all internal cables feeding audio signal should be shielded, and this is a measure which prevents audio signal from picking up noise from the environment. As I said before, it's very important that the shield of the cable, of the shielded cable, gets connected to the central grounding point on one point only, on one end only. The same for the shielded cables connecting to equipment together. So, for example, the shielded cable connecting the preamplifier with the power amplifier. I strongly recommend to utilize a shielded cable where the shield is connected to ground on one side only. This again to avoid ground loops. I didn't say before, but maybe it's obvious from what I said before. It's very important to shield all the power supply sections. Ideally, it would be great to implement a copper or aluminum shield between all the power supply section and all the rest of the circuit. Also, it's very important to try to maximize the distance between the power transformer and the smoothing impedance and the output transformer. This is because both smoothing impedance and especially output transformer can pick up electromagnetic field radiated by the power transformer. Of course, as it's very difficult to get a decent distance between the power transformer and the output transformer, let's think, for example, about a power amplifier. So in this case, it's very important to install the power transformer rotated on at least one axis compared to the two output transformer. In this way, we reduce the magnetic coupling from the power transformer to the output transformer. Also, it's very useful to implement a shield, a magnetic shield, in the power transformer. You can see an example here. This copper strip is a shield which highly reduces the electromagnetic field radiated by the power transformer. In all my projects, I do the same on the smoothing impedance as well. You will remember we spoke also about the hum, which can be picked up by preamplifier tubes mainly, which are mounted outside the chassis, so they are exposed to the external world. Well, in order to get rid of this hum contribution, we suggest to implement tubes shields, like the one you see now. Those shields are of course beneficial even if the tubes are mounted inside the chassis. In this case, the shields protect the preamplifier, especially tubes, from any magnetic field within the internal part of the chassis. So we have seen several steps, several actions which together contribute to creating a completely hum-free amplifier. Those come from the literature and from my experience as well. I hope you found these two videos interesting. Thank you very much for your attention.